So the examples were cut off of the presentation that I had initially done. So I want to run through them just for anybody who missed class, just to make sure they're recorded as well. So we ran through a couple of examples of the equations that we just went over in the previous presentation. So this is just reinforces using the gamma constant, how exactly it is manipulated for something that may not be the exact units that the gamma constant is written in. It's commonly had, MR per hour per 1 millicurie at 1 meter. But what happens if you have a source that is, much larger than 1 millicurie or at a different distance than 1 meter? That's where you have to manipulate it using just some algebra and some of the inverse square law. So the first step really is just adjusting for activity. This is an iridium 192 source. This is commonly used in activities at about 10 curies for HDR treatments. So we know the gamma constant. Again, if I ask these questions, I'm going to give you a gamma constant. I don't expect you to memorize things like that. But the gamma constant is per millicurie at 1 meter. We have 10 curies, so good to keep units the same. So first thing I would do is take activity and change it to the curie, change it to millicuries, because that's what we're given here. And so really all you have to do there is just multiply this factor by the activity that you have, which is 10,000 millicuries. And that gives you a dose rate of almost 6 R per hour at 1 meter, which is what we'd expect. These sources are very high intensity. So that, it's good to do sort of a gut check on these to make sure your answers make sense. If you got an answer that was below the millicurie value, that should give you pause, because you're saying, okay, well, I have a much larger activity source. I should expect a much larger dose rate. And certainly that's what we got here. Okay, so for inverse square, let's pull up the equation. It's really any of these questions you get are going to have to give you 3 out of 4 of the values, or make it such that you can figure out 3 out of 4 of the values, for, I guess, a more complicated question. But essentially, it really just involves taking the one unknown value and isolating it, which you do with a little bit of algebra, keeping your units straight, making sure your units are established cohesively early on. You want to make sure your distances are in the same unit, your dose rates or your intensity rates are in the same unit. But essentially, you take this unit, you take this situation, you have a dose rate at the isocenter of a LINAC, 600 rad per minute. There's always going to be an initial distance. I know the isocenter is confusing to have a distance, but you need to have that distance 1 in order to know distance number 2. So a lot of these questions will have be set up this way, where that gives you that distance. Well, we want to know dose rate 3 meters away. So you have a dose rate at 1 meter of 600 rad per minute, and you want to know I2. So really what you do is you just got to get I2 by itself on one side of the equation, which involves just dividing by 3 meters squared, or 3 meters squared, or 9 square meters. And that divides through, so your meters squared cancels, and you are left with 67 rad per minute. And again, I look and say, okay, well, I'm further away. My intensity went down. That makes sense. Sure enough, I could be confident in my answer. We also want to talk about half value layer and mu. So we know that these are linked very closely through this equation, and that means that all you have to do is just sort of plug in the values. Just a little more in-depth on mu. I had mentioned that it's called the linear attenuation coefficient. It's essentially how much radiation drops off per centimeter of material that it passes through. That's why the unit of inverse centimeters is kind of hard to think of an inverse distance. Distance is very easy to think. You could look at distance, but inverse distance is it's something per distance. So this value is the percentage of the radiation that drops off per centimeter. So for this situation, you have about 11% of the cobalt-60 radiation is being attenuated per centimeter of the concrete in question. But what it's asking for is half value there. So that's simply just plugging in these numbers and getting your final answer. And you notice that when you divide through by an inverse centimeter, you then flip the unit and you get centimeters, and your half value layer should be in centimeters because it is, you know, that's what you're looking for. It takes 6.05 centimeters for the intensity of a cobalt-60 radiation to be cut in half, at least in this specific situation. There's lots of different grades of concrete. You'll often hear heavy concrete used because that just has more stopping power. You get more bang for your buck in terms of distances used. Okay, and so sometimes we'll just be looking for number of half value layers. And this question is an example to really just drive home exactly what the half value layer is. So there's a little bit of extraneous information in this. But it says the half value layer for 6 MV photons in heavy concrete is 7.5 centimeters. Our weekly workload results in an estimated dose of the barrier of 100 millirad per week. How many half value layers are needed to reduce the weekly workload to less than 10 millirad per week? So, you know, like I said, 6 MV in this situation, the 7.5 centimeters for the half value layer is not needed because all it's asking for is how many times do you need to cut 100 in half to get below 10. So that's something you could do on your hand. You say you got 100 to 50, that's one half value layer. 50 to 25, that's two half value layers. 25 to 12 and a half, that's three half value layers. 12 and a half to 6.25, that's the fourth half value layer. Look, you're below 10 mrad per week. So the correct answer for this question is 4 half value layers. And that lets you know that 6 MV and 7.5, they're unnecessary in this situation. However, you can ask this question a little differently. And you could say, how many centimeters of heavy concrete are needed to reduce this dose to this? And in that situation, you could say, okay, well, 4 half value layers, I know that each half value layer is 7.5 centimeters. So I take 4 times 7.5, and that gives me a distance. That would give me a certain number, I believe, off the top of my head, 30, that would give you 30 centimeters. So that would be the answer in centimeters. It would be 30 centimeters of heavy concrete will get you to less than 10 millirad per week. So that's how that's used. So those are the equations. Those are the questions we worked through. I know I didn't include them on the initial presentation. I just wanted to make sure that you all had access to them. I'm going to be adding them to the YouTube channel, and so you can review them on your own. Thank you.